Halo cek, halo, udah cek tuh koro. Halo cek, halo, ready.
Hello, check, check, audio check.
point. Oh, okay. Try that one. If it works. Not enough space. Then we may remove that. It doesn't. It isn't on. That's not on.
It's on. It's on right now.
Oh, oh. That's on. No, it doesn't work. It doesn't. I'll use on the point. Okay. I'll use on the point. That's good. Okay. Hear me? And now, can you hear me? Okay? Can you hear me? So, do we need a microphone at all? The microphone is off, then we are all right. Yes. I'll raise my voice, okay? In front of you, you will have a trouble because it will be very, very loud. Should we start or should we wait for people to crawl in?
We wait for 5 minutes.
5 minutes? 5 minutes? Okay, then I have to sit. I cannot just stand here.
You can give us some jokes then.
So, I'm a comedian. I don't do jokes by...
But everybody is happy when you come to the stage.
They're happy. Okay, good. Good. We like Indian happy students.
There are another 3, 4, 5 minutes left on the stage.
can understand them. I didn't want to wake up. Yeah, I had some food. I didn't want to have breakfast. I had eaten a lot. Same time? Well, my different flight they will arrive on the same time. Well, my flight will stop at another place, so they will stop off. And, no, it stops on Kochi or somewhere, and then it goes from then 15 minutes. 15. Stop Bangalore? Huh. The other? Yes, okay. Yeah. Yes, mine is Air India here. From they want to get there. Thank you, Natesh, for inviting me to give a talk in this fantastic place. And now I think we are in a little bit more proper place to talk about. So there's no construction to distract us. Okay, so let's have an agreement that in my talks and yesterday also, today also, and in general. You can interrupt at any time because we are a smaller number of people. Then I'll stop and answer your question. But your questions must be more or less relevant to the subject I am talking about. Okay? Okay, if you can keep it in some frame, that would be good. Okay? Agreed? So, this talk is about about tools in the program code for CRY-EM map fitting and analysis. In fact, this talk is by Paul Emsley, and at the moment, if you look at his picture and my picture, my face, you will see some differences. And when you have a very low resolution CRY-EM and you use models, you may get this type of a wrong map. Okay, so. You try to reconstruct a protein named Paul Emsley, and you got a protein named Garib Nurshidov. Okay? There are some slight differences. For example. Okay? So, COOT is the original design for crystallographic calculations, and it is named already suggests that it is crystallographic object-oriented toolkit. It is for crystallography. It is not for crystallography, it is for macromolecular crystallography. And I think some of you at least may be aware of COOT, and it is used at the moment very, very widely in the field of macromolecular crystallography for map interpretation and model analysis. As I said, the aim of this tool is to interpret electron density maps generated by X-ray. It has a basic modeling tools that you can rotate and translate any rigid groups and to fit into the map, and it can do rotamer fitting, and it can do some refinement, regularization, and so on. Okay. I think in recent years, as I said, that because of very rapid advances in electron microscopy, could also needed to be adapted to the field. Strength of the COOT is it says that it was around 3.8 angstrom, but at the moment people are using at lower resolution. And seeing side chain and pyramids and so on, if you see them, you can then fit them properly. But in cryo-EM at lower resolution, you will see that you will not always be able to see side chains or pyramids and so on. And it does some analysis that local feeds that it uses a cross correlation function that yesterday we discussed a little bit about, and it uses a local cross correlation, and that how well your model fits into the electron density or electrostatic potential that is produced by cryo-EM reconstruction. And in few years ago, as I mentioned yesterday, there was a huge advances in cryo-EM reconstruction, and one of the first structures I think was a yeast mitochondrial ribosomal subunit, a large subunit, and it was published in a magazine. And the tools I'll tell here. They are described, most of them are described in this paper also in Acta Christ, and if you want you can have a look later, just say what are they. And this paper describes tools in COOT as well as tools in RefMag, as well as additional tools we had to develop for model building and refinement at high resolution. I think that somebody will collect, I hope, tutorials, so you don't have to make pictures. You can have a look at tutorials later. Okay? You can if you want. And there's no secret. Somebody, I'll give. Is anybody collecting these tutorials? Not tutorials, talks. Anybody? Somebody? Natesh? He's not here. Yes, you? Okay. Later I'll give them a tutorials not tutorial talks, and then. You can distribute to everybody, okay? Or you can take from them. Okay, without a further, okay, now I'll continue. And high resolution of cryo-EM of mitochondrial ribosome was quite spectacular, and we could see a lot of details, and almost all proteins and all components were visible, and at least for ribosomal field, it was very important, and for the field of cryo-EM reconstruction, it was one demonstration that how much advances has been made in the field. Before high resolution advances in few years ago, cryo-EM maps were usually like blobs. People call them a blobology. They are blobs. They may or may not be may or may not be correct. And validation was then even more concerned than it is now. And the main purpose of the tools in Qt was just to help to analyze to a certain degree these maps, and that is some of these tools are available in Chimera, but Qt was also able to do some of this visualization of map versus model and so on. The tools like that. And it also had a so-called partitioning maps, also map segmentation, and the idea of that map segmentation was put in polymously, in fact, implemented the algorithm described by Printil in 2010, and that is available as a plugin in Chimera. It is called Segera, as far as I know. The basic idea of this map segmentation is like that. You have let's consider it one-dimensional case. You have a map, and you cut at certain contour level, and then look at the higher level of look at the section of maps at a higher level than certain contour level. In this particular case, let's say that we cut at this contour level. Then we have only 1 point. Okay, and then if we cut at these two contour levels, at this contour level, then we look at the connected regions. If we cut at this contour level, then we'll have one connected region and another point that is almost connected region. And then if we cut at different contour level, and then we see again two different connected regions and two different connected regions. At the end, that will be our segment number 1, that will be our segment number 2. Okay, that's the basic idea. Basic idea is that at some contour level, you just try to find the connected regions. Okay, that works to a certain degree. And the algorithm uses a so-called I would call it a multi-resolution approach. That is called it's called a little bit different. The idea is that you have your map, and you use that map, and you use different levels of smoothing of that map. And one way of smoothing map is just adding b values into your Fourier coefficient. Yesterday you remember we looked at that. Now, when you add b values, map becomes smoother and smoother. Okay, and when you remove b values or sharpen, map becomes more sharper and sharper. At some point, you lose all features. So, that segmentation is done at different smoothing levels, and different smoothing. It is let's say that shows different features. So it has a higher resolution, a bit lower resolution, very low resolution. And segmentation would depend obviously on these levels. And you could segment at this level, and then you will have many different segments. And then you go from this level to that level. You don't throw away what you have done at this level, but when you go to that one, you just combine different segments. This way, you have segments that are more or less hierarchical. If you have two different segments at one level, if you go higher, these segments could be joined together. It would be unlikely that the two segments will belong to other segments. Okay? Does it make sense? It makes in principle sense that in a sense that if you have a protein may have domains, yes, and if you have, and then you can go to you have domains, proteins, and then subunit complexes, and so on, so on, so on. Yes? And it makes a sense in terms of the structure also. Okay. Any questions about this part? It could be used in Qt, and could give you some things like that. You may have segments like that, or segments like that, or and if you have models, then you can fit models into different segments. One of the purposes of segmentation, probably in your case, it may be helpful. Yes? You can just segment and then try to fit atomic models into different segments. But I should warn you that segmentation is way of classification, of way of clustering. In general, it doesn't. There's no general solution. And if you have a subunit complexes, let's say, if they interact very strongly with each other, then it would be very difficult to segment them into different subunits. Okay. And moreover, if you have a low resolution maps, and it's very likely that your map will be blurred as well as will have noise. And those noises may either divide segments into two parts, or they may connect segments. When you do use segmentation as a modeling tool to fit your atomic model into the segment, then you have to be careful. You have to analyze your data very, very carefully again. Okay? And validation will be always concerned. It's always like that. The lower resolution, more validation tools needed. Lower resolution, more analysis, and it should be more careful. Okay? I'm all right so far? Any questions? Yeah? No? Nobody? Yeah. Okay, I understand it is the last day and you want things to to get over everything, just go away. Okay? It's the last day. I want that whole thing. Okay. Okay, so now this higher resolution structure, Paul added a few more tools into code to help for map interpretation. And one of the tools is a jiggle fit. It has a nice name, very catchy name, and the idea is what is jiggle fit? In principle, the idea is that to find to do a six-dimensional search. The idea is how do I translate the atoms to fit the map? It's a six-dimensional problem. It was used there for ligands and solvent molecules and before. Now it's extended for any selection of atoms, or for example by chain, or you can select a different groups or loops or something like that. Let's say that your molecule in a certain position at the moment. Yes, let's say that helix. You go to code and have a look at your map and say that I want to fit helix here. Or you take your domain. I say that it has to be somewhere here. Okay, and then you say okay, try thousand different position and orientation of the molecule. You rotate and translate different thousand different orientations and translations. Okay, and then do a rigid body fit for each of them, and then rank density fit scores, and for each result you just scores that how well that particular fit describe the map. Does it make sense? Good. The convergence is sufficiently large, and if you use a low pass filter, essentially it means that you use only low resolution maps, then radius of convergence may be sufficiently large. Here's an example. For example, we have a double helix, and then we ask the code to put this helix somewhere here first, and then say that a jiggle fit. Yes, and then from here it can move here, and then you put atoms in their position. It is describes the map sufficiently well, and was used in interpretation of maps for ribosomes. When the ribosome has a lot of RNA. So, here then just to show that it works sufficiently well for the different resolution. Here are different cases at 3.4, 5, or 6.8 angstrom. And for all of them, it seems that the success rate, if you move your molecule by 2 angstrom, then success rate is very, very sufficiently high. Obviously, as resolution goes higher, the higher, the result, the success rate is higher. So as distances go, distances of the map to the true of the model from the true position, it goes larger and larger. Success rate goes down. And when current position of model is far from the ideal position of the map, and then success rate may go down by to 20%. At least in 20% of cases, it will give you some results. You can try different trials, and then you may get some results that then you have to visually compare and see that if it is good or not. Okay? Yes. Yes, jiggle fit is it is iterative precision. Yes, you have a model. Yes, for each jiggle fit. Yes, for each square or circle or triangle, you do a iterative fitting. Yes, you just move. Let's say in this particular case, you move a certain distance, that is 3 angstrom. Yes, and then you do jiggle fit. And jiggle fit is 1,000 cycles of rigid body. Rigid body with different position and orientation.
Then the next round I can take this one as a starting model and
you could do, but then it would have been better if you would use, let's say, 2,000 or 3,000. Yes? They are not dependent. It doesn't remember previous positions. Yes? And, you could think that if I've tried this position, next time I should not try this position. Yes? If you take 1,000 trials, yes, first 1,000 trials, you get some result, yes, and then when you do second 1,000 trials, you may try the same orientation and translation again. It would be a waste. Yes? But if you do in one go 2,000, then it may give you a better result. Yes? But what you can do is that you can try different resolution. Yes? You do jiggle fit and then change resolution, jiggle fit, change resolution. Yes? But according to this graph, this resolution is not that important. Yes? And it looks like that according to this plot, it's much more difficult to find translation than orientation. Okay? In certain senses, it may make sense if you have helix. Yes? Helix, you can fit helix like that, or just shift and fit again. Yes? And you will have a similar fit. The false minimum for some of the helices translationally is higher than for rotational. Okay? Does it make sense? That's jiggle fit. Jiggle fit is a fancy name of a random starting rigid body refinement. Okay? Good. So using the jiggle fit, we can, let's say that we have now RNA or homologous proteins sitting roughly in the density. But it is not a result, fit is not ideal. So what we can do is that another tool that Paul implemented was so-called morphing. It has some similarity with jelly body, but it is not exactly jelly body. So how does it work? And for let's say that you have 100 amino acids in your protein, and for sake of argument, so that I can describe. So for each amino acid, it takes and says that okay, I'll rotate and translate and try to find the nearest best fit for each of them. Okay, for each amino acid and amino acid will have its own rotation and translation. Then you can say that okay, if you have a neighboring amino acid should move in concerted fashion. So you can take several amino acids together and say that what is a consensus movement for all of them. Okay, and you do for overlapping regions and say that For this set of amino acids, that is a best orientation and translation. This region, that is best orientation and translation. And then you will have in a way, more or less a soft body fit. It will be like similar to jelly body, but it works differently. Does it make sense? So for each subgroup, you do a rigid body fit. Find orientation translation. And then try to find a consensus orientation translation for neighboring residues, so that they should move as more or less concerted fashion. It would be unlikely that, unless you have some chemical reaction, it would be unlikely that if you have two amino acid number 5 and 6, it would be unlikely that they would move completely different direction. Okay? If they move, they should move in more or less concerted fashion. Okay? That tool assumes that you have you can see amino acids and so on. It should be around let's say that after 5 angstrom, maybe 6 angstrom at some point. 6 angstrom I will be careful, but after 5 angstrom you could start using it properly. Yes? For 6 angstrom you need a longer range interactions. Yes? The jelly body works to a certain degree for 6 angstrom, but still you should be careful and you should compare, look at the map and make sure that what you have done is correct. Okay? Yes? The jelly body works differently. It works on, it's based on interatomic distances. Yes? It tries to make two atoms, yes, to move in concerted fashion. Any two given atoms within certain radius, and we use 4.2 angstrom, they move in concerted fashion. Here, first groups are moved, and then after movement, tries to make sure that they move in concerted fashion. Okay? They work a little bit differently, but the essence is same. That what you want is your molecules to move atoms or residues close to each other to move in concerted fashion, but they may move a little bit differently. Okay? Let's say the one amino acid could move a little bit more, another could move a bit less. Yes? And when you have a deformation of a beta balance, yes? Some amino acids will move more and others will move less. Okay? Does it make sense? But they should move in concerted fashion. It cannot happen that two neighboring amino acid residues, they move in different directions completely randomly. Okay? It would destroy your... sorry? It considers the concerted fashion idea after first fit. First it fits and then makes sure that they move in concerted fashion. Okay? You could do also that you could do like that. Yes? You could first, when you move, you may try to make sure that they move in concerted fashion. Okay? Or you do a first move and then say that they have to move in concerted fashion. Okay? You see what I mean? I'll explain here. Yes? But here what you could do is that you could say that this atom and that atom should move in a concerted fashion. Okay? And when you put between them I call them plastic strings because they could move a little bit differently. Yes? The string that could become longer or shorter. Okay? And then when one moves and it pulls another one with itself, and another one moves, it pulls that. If that moves, yes, if that moves, it pulls that one with itself. Okay? And that pulls that with itself, and so on. All of them move in concerted fashion. That is when you do optimization, details. When you do optimization, you make sure that they move in concerted fashion. Yes. And another way you say, look, let it moves. Yes. And I move that, I move that, I move that, I move that. Yes. It may go too far here, it may go a little bit less, yes? Then I say that they should move more or less in concerted fashion. Let's make a movement, a little bit backtrack of some of the movements to make sure that they will resemble what is a protein. Okay? It takes a amino acid. In principle, at the end, a cis trans should stay. In general, probability of cis conformation at the end, they are a little bit about cis trans peptide. Probability of cis conformation for non-proline is extremely small. For proline, is I think around 5%. It is safe to assume that when you see a amino acid, it's safe to assume that you have a trans conformation. And when you have a low resolution, yes, you unless you have proline, you have to put trans conformation. Okay? Because you don't have enough data to say that you have cis conformation. Does it make sense? Did I answer your question? Okay, thank you. Okay, now here's an example. Yes, this amino acids. They move for each of, you see that each of them move to a certain radius. Movements are in reality are not like that. It's just a little bit showing that the arrows or these yellow lines are longer than they should be. But then that's the idea is to demonstrate. Yes. When you do first, it does move this atom, that atom, that atom, this atom. Yes, you see that these two atoms move in a different direction. But we would expect that that should move similar to that one, and so on. Yes, and then now each residue moves, and then each residue moves, and then that algorithm works. Yes. I will not go into the details. As I said, that tries to make sure that a neighboring residues move in a concerted fashion. There's an idea of using a so-called robust analysis. That let's say that you have 5 residues. Yes, 4 of them are moving in certain direction, and one of them moves a completely different direction. Yes? Then you say that movement should be discarded. I have to rely only on 4 of them, because one of them is it's impossible that one of them will fly away. Yes? They are not independent. Does it make sense? Yes? It's rotation and translation. Yeah, for each amino acid, you have a certain rotation and translation. Yes? And then obviously rotation and translation can be converted to movement of atoms. Okay? So for each atom you have that, and then so on. Yes. What was the question, by the way?
Actually, when you're moving in a particular chain, does it mean all the atoms move the same distance?
No, not in particular chain. Not all atoms will move in the same distance. If it would be like that, then you would have only translation. Okay? If you would have only rotation of all of them, yes, then you would have only rotation. Yes. But the idea is that you not only have a rotation and translation, you have some deformations also. Okay? So that we say that for neighboring residues should move in concerted fashion, and for each residue you have that. Yes. Okay? Let's say for residue from 1 to 5, you have a concerted movement. That applies to one of the residues. Okay? And then from 2 to 6, 3, 4 to 7, and so on, that for each time you apply for different residues. Okay? And one of them will move more, another will move less, and so on. Does it make sense? So they don't have to move in the same amount. If they would move in the same amount, in terms of translation or rotation, yes, it would be rigid body. If everything moves in the same way, either rotationally or translationally, it is just rigid body. Okay? Yes. again, here it uses a cross correlation. Correlation, pardon. Correlation. All CUT optimizations are based on correlation. At the CUT side, that it's scale independent. Okay. Okay. After this morphing, you have to go to RefMag and refine and then analyze. It may deform your structure a little bit, but if it goes into right direction, then it's fine. Yes? And when you apply to crystallography, it doesn't update map also. So you have to go to RefMag and recalculate map and come back and then do it again. Okay, yes?
So say in these are NSST, you are moving this calibration, say n plus 3, not n plus 2. That makes a hydrogen bond or salt these something. So do you can you keep it weighted like I should maintain the hydrogen bond?
No, here you don't do that. You don't do that. Hydrogen bond. If you problem is that sometimes hydrogen bonds could be made and broken. Okay. Sometimes if you keep hydrogen bonds, yes, you lose certain flexibility, obviously, and you restrain to reduce the flexibility. Yes. It doesn't apply, as far as I know, that hydrogen bonds. Yes. That would be extra things to apply. But in jelly body, it tries to keep hydrogen bonds because it is intrachain hydrogen bonds, because it is dependent on interatomic distances. Yes? And the hydrogen bond can be recast to a certain degree at the distance between two atoms. Okay? Yes?
During this rotation translation, do you give additional weighting for theoretical restraints, like azimuthal angles?
No. They are implicit, not explicit. Implicit in a sense that you move now you have your certain conformation, yes, and you move each residue, yes, and then you try to make sure that the movements are smooth. Yes? If movements are smooth, then it's likely that many torsion angles will stay intact. It may destroy, deform your molecule. Then you go to the FMAC, for example, do a fitting and idealization. Okay? Okay? Should I move on? Thank you. They're very nice people. They agree immediately that I should carry on. Okay. So, here's an example. Yes? Here we have a loop. Yes, we have a loop. It is not in the map yet. And again, when you do that morphing, it moves to certain towards the map, and then it moves towards the map, and has to be done. This movement has to be done iteratively. After a certain number of iterations, it fits and cannot move anymore. And here's an example of morphing for. It can be applied for protein, for RNA, DNA. It doesn't matter. Yes? And here's an example of that RNA we try to fit, and that is I think from ribosome structure. And the zero cycle is like that, and then moves, and at the end, finally, you get a sufficiently well fit into the map. Okay? And you see that the conformation of this one and that one are not very different. They are more or less same. Okay? That tries to keep a conformation intact. Okay, another tool that is I think is used in crystallography and in EM is that a fitting helix. And according to Paul, not only according to Paul, helix fitting and other tools in CUT, some of the tools in CUT, use the map according to some aramesty, certain level of aramesty. And in EM maps, and it is assumed that a distribution of map points has is skewed as some certain histogram. And then using that histogram, it would decide that there it should cut. And it should cut at some point here. But if you look at the maps from EM, and you know that EM reconstructed maps are mostly empty. Mostly empty. There's a box, huge box, And in the middle of the box there's a map. And most parts should be around 0, but because of Fourier series things, that is not at 0, that's a little bit less than 0. So there's a huge number of points that has almost 0 values. Okay, so histogram is not doesn't reflect a histogram of the real map you would see. Okay, does it make sense? In crystallography, what we have is that we have a protein, yes, and then we have solvent. We have protein, solvent, yes, and they are protein and solvent. Both of them are real physical entities. Okay. In EM, after EM reconstruction, what we have is that a map and empty space. Okay? An empty space is not real physical entity. And only map is real physical entity. Okay? So we cannot use a empty space, that is empty space and a map, and say you cannot calculate the histograms and say that histogram will represent a real histogram. Okay? Because empty space will have a more or less 0 values. Okay? So number of 0 values will be very large. We will not have as smooth as in this case histogram. Okay? Because in empty space that is not physical entity, and there are a lot of zeros. Okay? Kut is identifies these 0 values and then removes them. And then uses a new histogram to decide where it should use this part of the map it should use for helix fitting and other things. And that's one of the reasons why when we go usually when you have a crystallographic maps and you look at the 2F minus FC type of maps, you usually cut around 1.5 sigma, and then you try to interpret around 1.5 sigma. When you have EM maps, sometimes you have to go to 10 or 20 sigmas because RMS calculated is not real. There are a lot of zeros. Okay, that's the reason why we have to change those labels, and that causes a certain problem in other places. But it is I will not stay on this point. Okay, does it make sense? Do we have a question? Do you have a question? No? Good. So after deciding that what is the contour level should use, and then it looks at the certain contour level, and it says that he has a certain contour level, and then takes helix, and puts in different orientation and translations, and looks at the scores. Yes? And then looks at the scores, and if there's some maximum of the scores, and then says that's very likely to be a right orientation. Yes? And a helix fitting could be used at different resolution again. Obviously, at high resolution, since you see a size change, the fitting would be much better than at low resolution, where you don't see a size change. It says it's 6.8 angstrom, but it seems that there's some element of size change here also. But probably it is higher than 6.8 angstrom. Okay, at 5 angstrom, the ideal max, you would see some size change, and that would help to fix a helix position and orientation. Okay, does it make sense? That's helix fitting tool. So, yesterday I talked about external reference structure restraints and additional restraints, and could have these tools also. And these tools could be alpha helices or RNA, DNA, RNA, A form of P form of DNA, and so on. You can put a particular interatomic distance restraints for this type of features of a molecule. You can add delayed restraints, and yesterday I gave you a script you can put into the code, and then you can use that extra restraints, and there are options to go through. And you can also input from ProSmart, and you can also interact with ProSmart also. And then these restraints could also be written out for later for refinement with RefMax. And that's very simple. That you have a helix here, and then you say that okay, I want to put these interatomic distances between these atoms. And as you see here we have a mostly hydrogen bond restraints, but you can add more restraints. And helices and strands are usually defined mostly by hydrogen bonds. And you can put these restraints, and they would be used in refinement in crude, and as well as you can export them for RefMax also. And ProSmart is a program that compares two molecules without sequence based on structure only, and then it writes out interatomic distances, distance restraints. Yes? And that is used in RefMax. Yesterday I told you that is a way of transferring high resolution information from high resolution structure to low resolution structure you are refining now. Okay, and that also can be used in code. Here's a protein. Let's say that you have a similar structure, and then you can calculate interatomic distances corresponding in the similar structure, and then some of them are white, and some of them are green. If you look at these structures, you see that although they are internal, local, similar, but there are conformational changes between them. Okay, one of them is open form, another is closed form. The reason is that there is a ligand here. So, what you would like is when you do a refinement, you would like to keep restraints where they are similar, but remove these restraints. Okay, they can be done in RefMax. They are done one way, and they can also be done by editing these restraints, and then you will have only those restraints that you trust, and that keeps the internal structure of a molecule intact, but it allows a conformational changes. Okay, does it make sense? No? Does it make sense? Okay, one person says it makes sense. Okay, you can then tell to other people. Okay. As I said, that they can use the program ProSmart that's written by Rob Nichols, and then you use interatomic distance restraints from a known structure to refine your unknown structure. But there may be conformational differences between them that you do not know. It may happen that during refinement, atoms may want to become to go further away from each other. Okay? What you want is that when atoms are close to each other, and the interatomic distances then it doesn't change too much, then you would like to keep them as in the known structure. When they want to become different, you would like to allow them to be different. That is done using so-called robust estimation. That means that you weigh down if the interatomic distance differences is very large between known and unknown structures, then you weigh them down. If interatomic distance, the difference between interatomic distance is very large, then weight is zero. Okay, so they are allowed to move apart, but they are not allowed to be different if they are locally very dissimilar. Okay, so you can have let's say you have two domains, they can move, yes, but each domain should be more or less intact. Okay, that makes sense, yes, in general. Sometimes obviously you may have that when domains move, that each domain also will transform, yes, but even then locally they will be intact. You cannot have unfolding completely. If proteins come to be unfolded, then you may be in trouble. Yes. You may not, but your protein may be, and your paper also. Okay, I'm all right so far. All right. So, proximal restraints they are represented in code like a spider web, and it looks nice. Yes. And it could be applied for proteins as well as for RNA DNA. So there's not much difference in terms of this technique. There's not much difference that what type of molecule we are dealing with. Could be protein, RNA, DNA, or something like that. Another restraint which Paul Zeber likes to describe is if you have a RNA, let's say, and stacking pairs must be more or less parallel to each other. Okay? How to make them parallel to each other? There are different ways. RefMath has one implementation, and here Paul describes implementation in code. So we have one plane and another plane. They must be parallel to each other. So these things must be parallel to each other. If during refinement, they should stay parallel. If they are not careful, they may get distorted and may have a not very nice RNA DNA geometry. We don't want that. Okay. So now let's say that now we have two set of atoms. One set is in one plane, another set in another plane. You want to make that that plane parallel to that plane. The one way of doing is that you pull these two set of atoms together, and then say that these two set of atoms must be on the same plane. Okay, and then bring them back to their original position like that. Okay. Does it make sense? You have this set of atoms, we say that that is on one plane, that is on another plane, but these two planes must be parallel to each other. It essentially means that if you pull them together, all atoms must be on the same plane. Okay? If you move all of them to the origin, and all atoms may be on the same plane. And when they are on the same plane, then you can pull them apart, and distance between them will be similar to the original one. Okay, that's one way of applying a parallel plane restraint. Okay, that is a type of RNA DNA restraints, the base pairs as well as the stacking restraints are generated so-called one of the programs that's called libg, and it's written by Fei Long. He works in my group, and those restraints are used in RefMath as well as in code. And for example, he has one example. We have a RNA DNA here, and you can put you can use libg restraints and represent that how these base pairs and the planarity restraint should look like. And then they can be applied when you fit this model into the map, or you do refinement. And restraints generated by libg for RNA DNA, the base pairing is something like that. There must be hydrogen bonding. Moreover, there must be there may be buckling or twist of bases, but those bucklings or twists should not be too much. Okay, so this type of restraints they are controlled by so-called torsion angles. Torsion angles allows a little bit more rotation of those planes. Allows, but penalize rotation of those planes with respect to each other. But allows a little bit of rotation. If the idea is that if map or electron density is good enough to say that there must be rotation or buckling, then this should be allowed. But you cannot have that two bases can go apart from each other. If they go apart from each other, too far from each other, then it means that there is no base pair. Okay? Then it should not be considered base pairing at all. And libg restraints are represented and visualized in code using very nice tools. I think that each plane is represented by a circle, and the parallel planes are represented using a vector between them. One of the latest tools in Qt is identifying cis and transpeptides, and in PDB there are a lot of problems that some of the cis peptides are identified wrongly, and they went to the PDB, and people analyze those cis peptides and say that PDB has a wrong structures in a way. In principle, you should always, when you refine, you should always check that if your cis peptides are real cis peptides. Many programs, including RefMath, they identify cis peptides, but if your model is wrong, then program may misidentify those cis peptides. Okay, and at the moment, should be you are responsible to check those cis peptides. Make sure that you are, if there is a cis peptide in the PDB, written as cis peptide, then there are really cis peptides in the corresponding to the data. Now Qt has this tool to identify and try to make force most of the peptide links. It forces to make a trans, and the difference between trans and cis is just a flipping of one of the flipping of the, let's say, the carbon oxygen around this line. And there's also proline and proline cis and trans, and probability of a non-proline cis peptide is around is very small. I think it is substantially less than 1%. Probability of non-proline cis peptide, but probability of proline cis peptide is around 5%. So you can observe more proline cis peptide than a non-proline cis peptide. So in principle, if you see a non-proline cis peptide, it's very likely to be wrong. Okay, but there are a few cases when it is right. Yes, but the likelihood that is wrong is very high. So you have to check it. Okay, and if you have a proline cis peptide, it could be right. It's a 5% probability, but you should again check. But as soon as you see non-proline cis peptide, you should panic and go to the density immediately. Okay? Agreed? That is for crystallographic calculation as well as cryo-EM calculations. Okay? Qt has now this way of new way of defining this cis and trans peptide, and when it looks at that it looks at this peptide bond, and if it starts to get distorted, and it will try to shift them. And there's a way in Qt it just gives puts rectangles, not rectangles. This is shape to say that something wrong in this particular peptide, and then you should try to check that. For example, you should here it is wrong because all atoms are not in the map. So you have to put them into the map, and then they will be removed. And Qt warns and gives now this new version of Qt, which you used yesterday, and it warns you that there may be some problems with peptides. Okay. And one of the tools in Qt is that yesterday I told you that in principle, in general, you should use a different sharpened blurred map. Sometimes you want to highlight some features of map. Sometimes you want to highlight the general overall features of the map. So you need sometimes to blur, sometimes sharpen. And Qt has this option, and for small structures, it works sufficiently fast. But if you have a very large structures like a cryo-EM maps, and you use MTZ files, then this sharpening and blurring works painfully slowly. Probably then you should use multiple sharpened maps, and use them or open them simultaneously. But in any case, it can give you some idea that how could you sharpen your map. Here's a map. Some side chains, and then you can interact with the sharpen, and you will see that side chains becomes more and more pronounced, and you can compare these two things. Side chains are less visible, and the helix is a little bit blurred, and if you sharpen a little bit, they become more, side chains become more pronounced. I should just re-emphasize that information content of this map and this map are exactly the same. There's no new information. Only the visual perception of this map and this map are different. But in terms of information, they have exactly the same amount of information. And sharpening should only be used for visual interpretation and visual representation. Okay, I told you that yesterday that there's a CUT mailing list. If you want to use some of the resources in CUT, then you probably should sign up to the CUT mailing list. That's on in the JIAC mail. And the Oliver Clark's Dropbox has something also. But I would recommend use that, or OCC4 bulletin board. And Polems thanks these people, and they are in our group. It was not me, it was the Polems. Okay? And thanks these people. These people are in Edinburgh, and they are in my group. And it would be surprising if I would not be in my group. And these are he was in Venkis group, now he's in Sweden, and he's still in Venkis group. Then he thanks Bernard. Kevin is in York, Bernard is in Sweden. And Jane and Dave Richard and Alexei Biden, I'm using Christian for some other tools. And I would like to thank you for your attention. Thank you. If you have any questions, I'll answer.
Thanks, Gariba. As I said, you are the most lucky people. Me being the organizer, I had to run around just signing your bills. Unfortunately, I cannot listen to you, but I will look at the video definitely, and I'm sure it will be a fantastic lecture, I think.
Okay. Any questions?
Questions? Jaydeep? Sarjit?
So I have it might be a common problem here, but I'm just giving an example of my protein, which is a kinase. So in kinase, the activation loop densities are very rarely seen even in crystals. So if you have two form of crystal, one is active kinase and inactive kinase, you may make out something. But in general, the activation loop is not very visible. So think about two problems. One, your reference has that density, but your map doesn't. Or your map has some density, but your reference doesn't, in that particular range. How do you tackle these two problems?
Okay. You didn't define problem, you define the situation, and there may be different problems in that particular situation. One way is that one way of interpreting is that what do I do with that if I don't see? Yes? Okay. Another way is that if I don't see, yes, and I put, yes, and should I use a interatomic distance restraint from the structure? Yes. Okay. And then you can have a different way of interpreting what you want to say. Is that what you want to say?
Yeah. I mean, if you have density, but your reference doesn't,
then you don't use interatomic restraints. You cannot use them. If you don't have, I would not use what I don't have.
No, that's what I'm saying. In those situations, you just do it manually to put residues.
You just put you put a manually, so okay. This loop, and there's a loop fitting option in code. You can loop fittings, and you cannot use it for reference structure because it's not there.
Right.
And in principle, if you don't see, you just don't put. Don't put. That would be misleading if you would put something there. Or you could put something with zero occupancy. It is also misleading. And there are new options that's coming in MMSIF, that you put some more or less reasonable confirmation, and then there will be a label saying that this part was modeled, was not derived
Right.
from the data. Okay? Okay.
Sorry, I missed a few slides, so I don't know whether this was there. It's regarding the restraints. Apart from the intramolecular restraints, there could be, like, we want to keep some intermolecular, say some RNA base is tagged with a tryptophan or phenylalanine ring, so can it be done?
LibG, yes, LibG can, when LibG works, yes, it doesn't care about chains, yes, it looks all planes in a protein and a ligand, RNA, DNA, yes, and then it considers all parallel planes in all of them, yes. ProSmart, when it generates, it looks only intra-atom by default. It looks only intramolecule restraints and intra-chain restraints. Yes? And in principle, there are cases when you should use a restraint between ProSmart. If ProSmart does, not ProSmart, restraints between different chains. Yes? And if ProSmart doesn't produce that, there should be an option. If it doesn't produce those type of restraints, then it should produce. And then in RefMath, if you use jelly body restraints, there's an option. This is not documented because I don't want it to be used by many people. And, there's an option to restrain, put a jelly body restraint between different chains also. But it is not recommended because the idea of refinement is to move atoms. If you put everything intact, yes, then they will not move away from each other. And there's an option also to define them manually. You see that between that and that and that. Yes? If there are few of them, let's say 5, 10, then it is easy. Yes? If there are thousands, yes, or millions, yes, then it is a little bit nightmare. You wouldn't like to do that. So there needs to be tools. Yes? If there will be cases that convincing cases that where it should be used, yes, then we can add a very simple. If we have not added yet, okay. Does it understand? For planes, parallel plane restraints, that is already there. For others, it might be there, but you have to do more work to activate them. Okay. Any other questions?
In crystallography, we use a lot of phase improvement techniques. What do you think will happen if we combine model phases with the lab application?
In cryo-EM?
Yeah.
In cryo-EM, at the moment it is extremely discouraged. You should not use model because okay. I can talk about that a lot, but I'll try to do as short as possible. There's a paper in Method and Enzymology that's already online. Yes, you could have a look on that. A refinement against cryo-EM. There's one section I talk about these things. Yes? And the reason is that you should not use crystallographic 2FO-FC maps for cryo-EM. The reason is that in crystallograph 2FO-FC is used precisely because you do not have phase information and you want to recover phases. Here you have phases. Okay? A phase combination. How do you combine phases? Okay? You could combine phases. Let's say that you want to put a figure of merit of phases 1. Yes? If you put figure of merit 1, no phase information, no combination will move that phase away from the position. Figure of merit 1 means that I trust these phases and they are exact and nothing can move it from its position. Okay? So it doesn't make sense then also. Saying that, that's crystallography. That's crystallography. For crystallography, you can't do that. You use a 2FO-FC. But there is a way of adding a model phase information to improve a maps. But the tools are different, okay? But they have not been implemented yet, yes? But even when implemented, they have to be with extreme care, yes? You don't want to add a bias into cryo-EM maps. In crystallography, we have that. In cryo-EM maps, you already have phases. Why do you want to distort it? Okay? Obviously, cryo-EM maps are not perfect. Or if they would be perfect, then you wouldn't need anything. Yes? And by the way, before we have enough work showing that what are the effects of using those model phases to improve maps, yes? You shouldn't use them. You have maps, you have observed maps. You should always consult observed maps. Never add a model information into the observed maps. Okay? If you add any information from model to observed map, you add by definition bias. Okay? Good bias may improve, but you may have bad bias. Then you can't prove almost anything. If you do things like that, then it's quite dangerous. Okay? You don't want that. Field is sufficiently clean, and that's one of the problems at the moment in cryo-EM, that crystallographers want to use the crystallographic tools to improve maps in cryo-EM maps. Don't. There are similarities between crystallography and cryo-EM, but they are different. In one you have phases, in another you don't. That is a major difference between them, apart from that there is potential. Okay.
Just curious to know, you showed one example with a closed and open structure can be, the closed one with the ligand, there is a restraint you can put, but it's just curious to know, even if we don't put this and the ligand is there, it shouldn't open, right? It should keep
okay. That is a different type of thing. In one crystal you have closed, in another crystal you have open form. Yes? In principle, it depends on how much movement is there when the molecule closed or open form, how much difference between them. Refinement may or may not take them. Yes? What I mean is that if radius of convergence is small, yes, then a closed form will stay closed, and then you cannot move too far. Yes? And if radius of convergence is sufficiently large, and then a closed form may become open form. Okay? We are after refinement. Yes? But when movements are very large, yes, it's unlikely to happen. When movements is a little bit, then it's likely to happen. If movements is very large and you can divide into domains, then probably you should search domain by domain first, and then you will have a let's say open form, and then you can do refinement. Yes? And I would not just put a open form to solve closed form, yes, and then hope that it will become closed. It may not. Okay? You should use your knowledge just to divide and conquer this work. Okay. Good, thank you. I think
one small question I have.
Yes.
So in crystallography we have this phases in the terms of angles, isn't it?
Yes.
Phase for each HKL reflection, and this angle is basically the phase difference between the interfering waves, isn't it?
Yes.
That's what it corresponds to physically. That's what it means in crystallography.
Yes.
And in EM micrographs, when we do a Fourier transform, you have the phase information in that. So physically, to visualize, where do we get that information? How do we visualize that physically? That
why do you get phases in cryo-EM? I think that question is to Ellen.
Not why. How do we visualize that there is a phase? We know that. That's what Aaron proved. So the phases are obtained from the Fourier transform of the micrographs, isn't it?
Yes, there's a lens, the electromagnetic lens, and that and she can talk about that more than I can, and better than I can.
I just want to visualize where do we get phases from in the from the micrograph.
Okay.
St. Garib is from the Institute of Crystallography. I do believe that he knows such name like Barry Feinstein. So, catalyze. And in general, it was ID and has been used for a while. In general, this ID to some extent has been used in EM analysis. When the phases were coming from the images at lower resolution, for example, catalyzed crystals, and the diffraction pattern was used, for example, in electron crystallography. And then the data have been combined, and then, in theory, you can extend. That was done. Strictly speaking, it was phase extension. To some extent, it can be used, and that's what, for example, was used phases from EM low resolution structure at 15 angstrom when Thomas Stiles got high resolution structure of the large subunits of ribosomes.
No, that is therefore combining EM and
yeah. Somehow the images or structures initials, they do provide phase.
Yes, I agree that, but his question was that where do you get phases in cryo-EM? Why do you have images? And
images by itself.
You have an objective lens.
That's what Aaron found. When you do a Fourier transform of that image, micrograph.
Fourier transform is a lens.
Natesh, when I'm taking picture of you, and when you're moving from the left to the right on this thing, it means what is changes, not your amplitudes. You are changing your own phases. When you're close to Garib, you have one set of phases. When you're coming here, it's the another phases. That's exactly, it's a classical teaching experiment. You have the image of the cat, and you have the image of the mouse. Take phases from the mouse, but amplitudes from the cat. If you will combine them, what you will get? You will get a mouse. Therefore, amplitudes are essential to determine which atoms are which atoms, but in general, position of all atoms are defined by phases. Therefore, image which provides you projection gives you some kind of initial, preliminary position. It's an approximation which you are refining during your procedure, but you are getting phases from the image. They're, ready to use.
Makes sense. That's what the session doesn't end without Dalin's question.
Okay.
I was wondering why he didn't ask.
Okay. Yes.
It's not a question. I just want to make one comment about Nate's suggestion about the phase. Since to my understanding, it's like it's different from physical phase or the physical waves. Since there's a long discussion about if from physics to ask crystallography, how can you determine phases? You can from equations you cannot. It's lost in diffractions. And how can you find it back? Actually, my personal from what I learned is the phase from physics concept is different from what we are talking. From what we are talking, it's a chemical concept. It's a mathematical concept. It's not a physical phase from the waves. Since our number is phase is relative. You define origin, you know the phase for certain position. You have to define origin by ourselves. But physically, the phase is physics. It's different. I just want to make comment.
Okay.
Look, no physics without any math. You cannot do physics without math. It's one story. Secondly, all these maths, so-called, and if you will go even for X-ray analysis, it's what we are trying to use in EM. You are trying to compare, and that's all this, if you like, maximum likelihood, K-means, Higgs squares, approaches, etc. It's a comparison of measured values with calculated or assessed measurements. You're trying to minimize the difference, what you have measured and what you have obtained during your approximations. You are doing minimizations. In which way and which algorithm is another story. If you like this one, use this one or another. But how you can separate physics and math, I cannot even imagine.
Very good. Thanks. That reminds me, I should advertise our institute.
If you want the biology, you have to do chemistry. If you have to do chemistry, you have to know physics. If you want to know physics, you have to do mathematics.
Yes.
Okay.
That reminds me to advertise our institute. Our institute focuses on undergraduate education, interdisciplinary. So first 2 years, everybody has to learn all the 4 subjects: physics, chemistry, biology, and mathematics. And after that, they specialize. Good. Thank you. Okay, let's go for tea and gather back in half an hour.
Okay, good. Tea time, yes?
11:30. Anybody who is leaving in the afternoon, they should collect their fee receipt from Monica. Okay? Monica is around somewhere here. Okay. Whoever is leaving tomorrow, then they can collect it in the evening. So. Hello. Probably, I don't know how many of you have realized this lecture hall is a sea view hall actually. Why it is named? Because it's not beach view. There are other lecture halls which is called beach view, which has only one side view of the beach actually. Here it's all the three sides sea is visible actually. So we have hidden it, but after the talk we will open it, okay? It's not visible. It's not visible from here, but it's only visible from there actually. It's only visible from there. That's why probably most of you would have not realized. That's why I'm telling that. Actually, this is a sea view hall. When you come inside, it was very good view, and we wanted to put the stall there, and that's why we put the screen here. If I had known that these people are not going to come, I would have put the screen there actually. It's open actually. It's the best view actually. In fact, it's the best view. Yes. We should be able to do it probably in the evening maybe. Evening there is no, so I can ask them to remove this probably. You can move inside and then we can have the best view in the evening probably. In the evening after 7 it's dark, that's also bad. But yeah. You can actually, after the talk you can go back and see actually. It's a very beautiful view actually, this sea view. When we came to inspect out of all the 4 lecture halls, everybody wanted this hall actually, and there was booking for 9th and 10th actually, and our organizer, he was very kindful to shift the venue to other lecture hall and then give us the whole time actually. Good. Let's get going. Everybody is back? Good. Yes, projector is at the back. Back projection. And yeah, we will open the window after that lecture, I think. It will be a nice view. So we have the last but not the least lecture by lecture 23 in this meeting, in this course. I would call it as a conference as well because everybody had participated very enthusiastically in all the practical sessions and also all the poster sessions. I'm very happy about the level of posters that have been displayed, and it was very good. And so to introduce Dr. Ardhan Patwardhan had been a PhD student in KTH Royal Institute of Technology. Suppose it should be in UK, isn't it?
Stockholm, Sweden.
Stockholm, Sweden, okay. And then he moved as a lecturer in computational structural biology in Imperial College. And I have seen him several times in the EMBO course. He may not remember, I was a student at that time, in the Birkbeck. And I was a welcome fellow at that time in Helen's lab. And then he moved, after being lecturer for more than 11 years, he moved as a project leader to electron microscopy, EMBL, EBI, and now he is a coordinator of cellular structure and PDB production in EMBL, EBI. And we have invited him to give a talk regarding the PDB deposition of electron maps and the coordinates, and he will talk us about the topic. Okay. Validation. Ardhan.
Okay. Thank you very much, Natesh, and the organizers for inviting me. And I'm very lucky to have, in a sense, the last talk because all the essential basics and everything is covered, so I can make some assumptions in terms of what has been discussed. So as Natesh said, I'll be talking to you about probably the last step in the process, which is when you do your publication, you deposit your data, and I'll be focusing on 2 of the archives, so EMDB and Empire. And I'll also try and focus a little bit on initiatives that we're doing in terms of validation. So I'll start by giving you a very brief introduction about who we are and some of the organizations involved, go through the status of the archives,
and then go through some of the web-based services that we have for EMDB and Empire, some of the ongoing initiatives we have with regards to validation and data integration, and then something about what we perceive as future challenges and opportunities as well. So if we look at who we are, so I'm based at the European Bioinformatics Institute, the EBI, which is a part of EMBL. But while EMBL has its headquarters in Heidelberg in Germany, we are based in Hingston, which is just south of Cambridge. And EBI is a major hub for bioinformatics resources with everything from genomes all the way to systems biology. Within this, we serve essentially the molecular and cellular structure resources. And the team's name is Protein Data Bank in Europe. So if you look at what we do, we maintain and manage the archives, PDB for atomic coordinate models, EMDB for 3DM reconstructions, Empire for 3DM raw data. And we also develop and maintain web-based resources for searching, visualizing, and validating data. We organize a lot of community-wide initiatives to drive issues forward, for example, on validation and cellular structure and so on. And key themes that we have are integration with other bioinformatics resources, to integrate structural data with other bioinformatics resources, but also to integrate information between different imaging scales from the cellular to the molecular, and also validation. So in terms of organizations, I'm just going through this quickly because it's you have an acronym soup when it comes to archiving, and it's just good to have an overview of some of these different acronyms. When it comes to the PDB, so the PDB is actually the name of the archive, and it's actually it's managed by the WWPDB, is the managing organization. The partners involved here are RCSP PDB, which is the archive keeper, along with us, PDBE, PDB Japan, and BMRB. And the way this works is that we have coordination of data deposition, so we work together when it comes to deposition of data to the archive, but then there's competition on data out, so we all have our own data out resources. EMDB and Empire are actually EBI resources, and they're both managed and kept at EBI. But the deposition to EMDB is coordinated via the WW PDB deposition system. So now there's an integrated deposition system for PDB and EMDB data. And you can deposit data at PDBE, RCSP, and the PDBJ sites. Empire, though, the deposition currently is only at EBI. You may have also heard of EM Data Bank, and just to make things more complicated, EM Data Bank is separate from the EMDB. So EM Data Bank is actually an NIH-funded project, and this was a project funded to Baylor, WACHU, PDBE, and RCSP. And the EM Data Bank project involves, it involved getting EM into the WWPDB deposition system, which is now done. And the second thing, which is ongoing, is developing validation for EM, including validation reports. So if you've been doing PDB depositions, you're already familiar with validation reports, and we're bringing that now to the EM side as well. So just to summarize once again what goes where, there is a strong consensus in the EM community in terms of that the final single particle map and the subtomogram average maps should go to EMDB. And many of the journals have mandatory requirements for deposition prior to publication. When it comes to tomograms, we have talked a lot with the EM community, with the relative stakeholders. we have not been able to get, the best we have been able to get there is a strong recommendation for depositing representative tomograms. And the reason is because the tomography community still feels that even after they have published things based on their tomograms, there may be other data there to be mined, which they want to mine themselves before opening it up to other people. So we try to move things along with the community rather than trying to push them into a corner. So we are trying to work with them to gently coax them into where the PDB and EMDB is right now. With fitted models, again, it's mandatory that this should be deposited to PDB. And with regards to raw image data, I think it's encouraged, but again, it's not mandatory to deposit the data at present. So just summarizing again, raw data goes to Empire, the final 3D reconstructions goes to EMDB, and the fitted models go to PDB. And I'll send out a PDF with the slides, and here I've just summarized some of the websites which might be useful in terms of accessing information about the different archives. So going on to looking at the status of the archives, if we look at EMDB and the number of entries being released in EMDB, the red columns here show you the cumulative number of entries, and the axis is on the right-hand side here. You can see that this year we'll have over 4,000 entries in total. So it's still small in comparison to the PDB, where you have 120,000 structures. The blue curve here shows you the number of entries being released per year, and the axis on the left-hand side. So you can see that already this year we have about 500 entries released, and if you see last year we had about 600 entries released in the full year. So we're looking at almost a doubling of the number of releases this year compared to last year. So we're already starting to see this starting to accelerate. If you look at EM submethods, so here we have blue represents single particle, red represents helical, then you have green for subtomogram averaging, purple tomography, and light blue is crystallography. And crystallography here is both 2D crystallography as well as 3D crystallography, what Tamir Gonen is doing. And what's, well, the dominant trend is that you can see that single particle dominates. But we have been really trying to work hard with the EM tomography community, trying to encourage deposition. And if you look at the purple and green curves, you can see that their proportion has been growing gradually to about 15% last year. But then again, we see this year, this has suddenly taken a jump to about 23% of the depositions are from tomography. And I think this is maybe partially being pushed also by the fact that now suddenly you start getting subtomogram averaging structures which are at quite high resolution. So we had this 3.9 angstroms resolution structure by John Briggs presented at the Gordon conference of the HIV, I think, eczema. If you look at resolution trends, so here we have different bands of resolution. I think what's you can clearly see the better than 4 angstroms band has been growing very quickly since about 2013, you can see. And you can see that the other bands are starting to be squeezed, so we can expect this is going to become a very prominent, it's almost an expectation in many cases that one would reach somewhere along these levels unless one has good reasons in terms of conformational flexibility or other reasons why it's not possible to get to these levels. And I think anecdotally, we know that this is probably being pushed by the introduction of direct electron detectors. And we can actually mine the data that we have in EMDB to look at this in more detail. So here we have released entries by direct electron detector. And the red curve here shows you entries, the fraction of entries by direct electron detector. And the axis is on the right-hand side. So you can see that last year about 45% of the entries had been done by direct electron detector. This year it's increased to about 70% of the entries coming out are based on direct electron detector studies. We can also look at so if you're interested in buying a system and you want to know what people are actually using in terms of types of direct electron detectors, this curve shows you different types. So it's a bit of a misnomer to call it manufacturer. So this is, the red is the Falcon, the yellow is the different direct electron models, and the green is the Gatan K2. And you can see that while initially when these things came out, you had the DEs and the Falcon was dominating. You can see that the K2 has started to increase in dominance. We can also look at the direct electron detector usage in terms of the high resolution structures. And here, again, the red curve shows you the fraction done by direct electron detector, and the axis is on the right-hand side here. And here you can very clearly see the impact of direct electron detectors. So from 2014 onwards, more than 80% of the structures are done by direct electron detectors. Again, if you look at the better than 4 angstrom structures done by direct electron detectors and look at the different models of cameras, you can see again here it's even clearer the dominance of the K2. The Falcon usage looks like it's on a downward trend, but we have to see what happens now with the Falcon 3 coming online as well. So with EMPIRE, so not everyone knows what EMPIRE is. So EMPIRE is the Electron Microscopy Pilot Image Archive. And the work that I'm presenting to you has been done mainly by Andrei Iudin. Because of the popularity of the archive, so when we started this, the idea was that it would be a pilot archive, but it looks like more or less this will become an established archive, so we're planning to change the P here, probably from pilot to public. It started in 2014, and it's essentially a archive for raw 2D image data related to EMDB. The usages include, the data can be used for validation, development, testing, teaching, and also for essentially for the safe storage of data. So I'm quite surprised often how many times people come up to me and tell me that the only place where they can actually find their data after some years is actually either in the EMDB or in EMPIRE. And I was also pleased to see in terms of development, for example, at the Gordon conference this year, so we had both Schorsch as well as John Rubinstein's, someone from working with John Rubinstein presented methodological developments, and both of these had actually used EMPIRE data to test things. EMPIRE is also used in the EM map validation challenge, which I'll tell you a little bit more about in a few slides. So when we started off, we wanted to work with the community, and we were not completely sure as to what people would want to deposit to us. So we were not particularly prescriptive, and we accept different types of data. So both the movies, average micrographs, particle stacks, and tilt series. Now, with EMPIRE, we really have a big data problem in the sense that these are large data sets. So the challenges are both storage as well as data transfer. And in terms of storage, we're not yet that big that it's become a problem. But we have issues with transfers because these are still terabyte-sized data sets which need to be transferred and so on. So we have tried to be as flexible in terms of providing different means of transferring data. Aspera and Globus are quite suitable for large-scale data transfers, and FTP, HTTP are also there for smaller-scale data transfers. So if we look at the metrics at present, the number of entries in Empire are about 56, totaling about 37 terabytes, and average size of the data set is about 650 gigabytes. There are 7 sets which are more than a terabyte and 1 set which is more than 10 terabytes. And I have at least confirmed with a few people that they have actually downloaded the 10 terabyte plus data set as well. In terms of transfer speeds, uploads are 1 to 2 terabytes per 24 hours. This is measured in Europe, US, and Australia. 2 exceptions that I know of. One is China. The other is EMBL Heidelberg. For some reason, we can't transfer data to our own mother site, but that's another thing. I would also be interested in knowing, for example, if there are people in India who have been downloading data, what types of rates, and if you have had problems with transfers, etc. We know that it's being used because there are at least 21 citations. And we also now have a Nature Methods publication, which we recommend people, if you want to cite it, then that's a good citation. If you look at uploads and downloads, so we have approximately 3 uploads per month, 3 users uploading data to us per month, but this is starting to accelerate, so we've already in the last month seen an acceleration of pace. This totals about 3 terabytes being uploaded per month, and on the download side we have about 70 downloads per month and about 30 terabytes being downloaded per month. If we go on then to look at some of the services available for EMDB and Empire. So I think this was shown, this page was, so this is the pdbe.org/EMDB. So this is the EMDB website, and this is sort of the portal for most of the information that you can get. These images are sort of quick links to different, some of the main categories of molecules. In the left-hand panel here, you've got links to the latest entries. So EMDB also has a weekly release cycle, so there's new data released every Wednesday. And you also you have an advanced search as well as browse functionality here. pdbe.org/mstats is a statistics service which gives you access to dynamic charts, which is always based on the current state of the archive. So we have general charts, charts on resolution, publications, and if you have ideas of things you would like to have data mines which can be done, then we can always add those to the list as well. So I'm just going to show you a couple of trends which might be of interest. So this is journal statistics. So here we have, I've highlighted 3 journals: Journal of Molecular Biology, PNAS, and Nature, and the number of publications related to EMDB entries. So if you look at PNAS as well as JMB, you can see the trend is essentially downwards. There are fewer and fewer EMDB-related publications there, whereas with Nature, you can see that it's going just plain upwards. So if you look at the number this year, it'll be somewhere around here, around 40 publications in Nature. We have a lot of resolution charts. I always try to caution here that the resolution that we are showing is the resolution reported by people. So if you tell us that your structure has a resolution of 0.001, unfortunately, we'll have to put that up. We'll ask you to try and change it, but we need your permission to change it. And sometimes people just ignore our emails. But I think since the scrutiny has, once people started to reach resolutions about 3 angstroms and better, there's been greater scrutiny. So at least in terms of reporting, usually the numbers being reported are the 0.143 criterion done by FSC. So there's at least some consistency there. And you can see some trends here. You can see sort of the initial phase, then around 2010, 2011, you see this small jump downwards here, and then you have these very high resolution structures now coming from the micro-ED, Tamir Gonen's structures. Okay, so in terms of visualization, we try to provide tools which allow you to look at data without having to download it. So if you can download the data, you can use things like Chimera and Coot, etc. to look at things. But this gives you a first quick glimpse. And we have a 3D viewer which is available through links of these sort. Unfortunately, our 3D viewer is based on Java, and given that there are fewer and fewer browsers which support Java, I think this is something which is unsustainable. So we are actively working on a WebGL-based 3JS replacement for this. What we also introduced last year is what we call the volume slicer, because we got lots of requests from people that they didn't want to look at the surface renderings of the molecules. They actually wanted to look at the slice data itself. And the volume slicer allows you to look at the slices interactively in the browser. And you can zoom it up into full resolution if you want to look at details. It also allows you to switch between the 3 orthogonal directions interactively. And keep in mind, it can give you views on gigabyte-sized data sets without having to download anything, so that can be quite convenient. For all the entries in EMDB, we also provide what are known as visual analysis pages, and these can be accessed via links of this sort. So it's pdb.org/dex-session-code/analysis. And this is our attempt to give as much so-called validation information. So I wouldn't really call it validation, but it's more sanity checking and essentially basic information that we can get from the entries. So we provide, for example, orthogonal projections, central slices, and you can double-click on a central slice to get it a zoomed-up view of it. This can be quite useful to look at just the quality of the map quickly. Also the orthogonal surface views. We also provide some curves which might be useful. So we have map density distribution. So here you got the log of the number of voxels versus the different bins of density on the x-axis. And as Garib showed you, so in EM, because you have masking and so on, so you get these very strong peaks at about 0 density. We also show you the volume estimate, which can be sometimes useful to look at whether the contour level which has been specified makes sense. So this shows the blue curve here, which is very like a step function. So the blue curve is how the volume varies with contour level. And if people have provided us with the Fourier shell correlation, then we show the Fourier shell correlation as well. We also provide rotationally averaged power spectra. So this is, I think, similar to in X-ray analysis, you're used to the Wilson plot, but here we have the log of the intensity versus the spatial frequency. And here I just have a few examples of how the rotational average power spectra looks for a range of resolutions. So here we go from a older EM structure at 30 angstroms going to 3 angstroms. And so if you look at the lower resolution rotationally averaged power spectra, you can see what we used to expect in the old days, which is essentially a falling off rotational power spectra, which looks kind of like this. If you look at the more recent structures, you often see things which look like these two curves, which is you see, first of all, you see a flattening off of the curve. So this is the the filtering or the correction which has been applied. And then you can also see these sharp cutoff, which I think Garib was mentioning, that can cause truncation effects and so on. And what I found quite interesting, because I was used until quite recently, we were quite used to having 20 angstroms maps and so on. But here at the high resolution maps, you then start seeing these bumps here. So you can see one bump here, and then you can see a second bump coming in here. And the same thing here. So these are sort of characteristic bumps for the secondary structure elements and so on, which now become much more visible in EM as well. If you have fitted a model to your map, we also do an analysis of how well the model fits into the map. This is not particularly sophisticated, so we look at, for example, the map at a certain contour level, and we look at the inclusion, how many atoms are included within the map density. And we do this on two levels. One is that we look at the full map versus model, and we look at how if we vary the contour level, how does the atom inclusion vary with that? You have a lot of red, but quite often you might have it mainly green and a few parts which are red, which allow you to quickly find loops and so on, which might not be that well fitted. We also, so what I've shown you up to now is things that are available for archive entries. We also provide standalone validation servers. And this is really as a convenience for the community, but also to promote use and reporting. So we want to get some sort of consistency in how people report things. And it also allows us to work with the community to develop standards and standards for capturing validation data. So one I think which is used quite a lot is the Fourier shell correlation server. You can upload two maps and it'll calculate the Fourier shell correlation. And it also generates a curve which you can download and then deposit to EMDB. One of the good features here is that it automatically calculates your thresholds, and we've also worked with the developers of Bsoft, Reliant, and EMAN2. So these packages now also they generate curves which can be downloaded and uploaded in your deposition. I guess you have previously in the course described tilt-pair validation, so I don't need to go through that. And tilt-pair validation was developed by Peter Rosenthal, and he developed a tilt-pair validation server in his lab, which we have now ported to EMDB. So this just shows you the tilt-pair results. So you get a summary result of the tilt-pair analysis, and then you also get a per particle result from the tilt-pair analysis. So you may have also heard about ResMap, which is a way to estimate the variation of local resolution in a map. So for EM, this is quite important because you can have one part of the map can be much better defined than other parts and so on. ResMap was developed at Yale by Hemant Tagare's group, and Jose Maria Carazo in Madrid has essentially developed a ResMap server. So this is developed in the Scipion package. And what he's done recently is that he's set up a web-based ResMap server, which is also available. So what we have done here is that we provide a link from our validation page to the ResMap server. So this is not online yet, so it will be online next week. But essentially, the ResMap server is quite convenient, so you don't have to download or install ResMap. You just need to upload your data to ResMap to do your ResMap calculation. You import your volumes, and I think as Hemant now recommends, in order to do your ResMap calculation, what's recommended is that you use half maps just like you do when you do a FSE calculation. So ideally, what you upload here is your unmasked half maps. The server will automatically calculate the mask. One thing which is important for ResMap is that it makes assumptions about the whiteness of the noise. So it carries out a pre-whitening step, and it has a wizard here which allows you to then see how well the whitening step has worked. So you need to look at that and adjust your whitening parameters. And then once you execute this, then you essentially get the full range of ResMap results. You get slices through your density, a color-coded resolution chart. You get a histogram showing you the different number of voxels in the different resolution bins. And it also allows you to download a script, a Chimera script, which allows you to overlay the ResMap results on your map in Chimera. So going on then to the Empire. So Empire now has its own website, which allows you to browse and download data, and you can also deposit data. And every Empire entry now has its own accession code, and the entry pages have you can browse and select data that you want to download. So you might not want to download the full 1 terabyte set initially. You might just want to download a couple of micrographs to have a look at them, which you can do through this page. What we have also done is that we provide thumbnail views of these images, which is again quite useful. You might want to look at the images before you actually download a multi-gigabyte image. Empire also has its own deposition system, and this is, if you're used to the WWPDB deposition system, this is different in the sense that this is user-based. So you log in as a user and you have access to all your depositions, but it also means that multiple users can share access to depositions. So you can have one deposition where the PI has got submit access and read and write access, whereas the PI then gives, for example, a student just read and write access. And also, just to make it more convenient to use, you can log in via Google and Facebook, and we are working on other single sign-on systems, so to make it as easy as possible to log into the system. You might also be familiar with ORCID author IDs. So again, to make this as easy to use as possible, we have been working with the European PubMed Central team in order to make it possible to harvest the information from your ORCID account, so you don't have to fill these things in manually. Okay, so I'll go over to talking to you about some of the ongoing initiatives and things which are happening on the validation front. And I think one of the main things is the EM validation reports. So if you've been doing PDB depositions, you're familiar with the fact that when you do a deposition, you get a validation report, and I think the expectation is that those validation reports will be sent when you send your manuscript off to a journal. You include your validation report as well. So this is now in production mainly for EM models, and we have generated validation reports for all PDB EM models as well, and these are available from the FTP sites. What we are working on right now is the map validation part of this, and as a starting point, we are essentially using what we have, what I showed you on the visual analysis pages. So it's the same functionality, and we're essentially limited by the data available, which is mainly stuff which allows us to do sanity checking. These things are already in testing, so we have them, but I think it'll be probably at least to the end of the year before these things come into production. So this just shows you some of the elements. For example, if the FSC curve has been provided, we can show the FSC curve, and then we have also a rotationally average power spectra that we show. And as I mentioned previously, we had the EM Data Bank Map Validation Challenge. So the idea with this was that we defined essentially a benchmark set of 7 data sets, Empire data sets, which correspond to these entries. People could download this data, and then the idea was that they would process the data, come up with new 3D reconstructions, and upload the maps. And the idea with the challenge was that we would then compare the results to see if we can learn things in terms of both what assessing the resolution and what the differences between packages in terms of coming up with reconstructions and so on. So if you look at the number of maps that have been deposited, so we have 66 maps, and the submission phase ended in April. And we're now working on examining the results of the challenge. So if you look at the 66 maps, you can see that there's a good spread in terms of the different targets which were used. But in terms of refinement software, it's slightly skewed. So majority have used Reliant, then followed by eMan and FreeAlign. At present, for the assessment phase, we are still doing this in a sort of double-blinded fashion. So I'm one of the people who is double-blinded. So I can't show you exactly what we are looking at, but which is why this stuff here is blinded. But I mean, these are some of the reported resolution for one of the examples, apoferritin, and the structure published by Chris Russo and Laurie Passmore was at about 4.7 angstroms, which is shown by the red line here. And each of these shows you one of the deposited one of the challenge reconstructions, and you can see we have a range from 3.1 angstroms to 6.8 angstroms resolution. What's I think even more interesting here is that this one and this one, so the best and the worst, have been done using the same software package. So this shows you it's not only the software package, it's also the people involved, and the workflow, and what parameters you use often to do this. So we are not only looking at quantitative analysis of this, we also want to do a qualitative analysis just to see what, by eye. So numbers are one thing, but you also want to see what features you actually see in these maps. So here, in order to do this, what we are looking at, so we've gone through the papers and we have tried to identify motifs and structures which the original authors highlighted as being important in the structures. And this is just one example where Chris highlighted that there's some extra density which was corresponded to 3 residues. So if you look at 2 examples of the challenge structure, so here's you got one which is at 6.3 angstroms resolution, and this is the unfiltered and the filtered map. You can see that first of all, so this is the B factor correction. You can see has very little effect on the map itself. You don't see much of a difference, and you also see that there's no side chain density, which I guess if you're an X-ray crystallographer and it's 6.3, you wouldn't expect anything. So it's in line with what should be the case. Here you see a 3.5 angstroms resolution structure, and here you can see that there is a good difference between the unfiltered. So you can see the B factor correction is important for the visual perception of things. So you can see the side chain density is more defined. You can then also go into things of, does the truncation make what types of issues are caused by, for example, truncations of in terms of the definition of the density, the truncation of the after B factor correction if you do sharp cutoffs of the density and so on. But as said, so this is still in progress. I just wanted to show you some interim results that we have. So similar to the map challenge, there's also ongoing model challenge. and the model challenge is slightly phase shifted in time, so it ended in June. It used the same benchmark set as in the map challenge, but the idea here was to fit models to the maps, to the EM density, and then to evaluate and compare the fitted models. And although the assessment has started here, I don't have anything that I can really show for the model validation challenge. I then wanted to go over to talk to you about some new ideas that we are looking at, and which have been presented by other people, but I think which are of interest. And one of them, which was presented at the 3DM Gordon conference, was by Gabriel Lander at Scripps. So he has something which he calls the dirty laundry server. And the idea with this is to see how well a map supports a derived model. And our idea is then that we are working with him so that for EMDB entries where an assessment exists in the dirty laundry server, we can provide a link from us to the dirty laundry page. Don't ask me. This was not my choice of name for the server, but it is his. So how does this work? So he starts with user-generated atomic model. So this assumes that someone has done a fitting of atomic model to the map. And what he then does is generate 100 models using Rosetta. And then from these 100 models, he selects the 10 best models. And then he refines the 10 best models using Phoenix. And then based on the 10 best models, then he looks at, for example, the RMSD between these to see which parts might be more consistently defined by the map density and so on. So just to show you an example of how this works, this is an example of the P97 ATPAs. This is the map density, and here you can see, even by eye, you can kind of see that maybe some regions have a different level of detail than other regions. So this is now with the 10 models, the ensemble of 10 models overlaid. And then if you look at the RMSD, you can see that the blue here is low RMSD, red I guess is high. And you can see that some of these regions here have high RMSD here and here, and these would correspond, for example, here, which look more noisy as well visually. This is just the same thing. So this is a regions of example of regions with low RMSD, and you can see that the models overlay quite nicely. And here's a region with high RMSD where you can see that the models seem to be all over the place. Another idea that we are working on, so one of the things which is sometimes overlooked is that when you look at these surface models, you're looking at them at usually the recommended contour level, and that's what's being provided to us by the depositors. But we know from before that these values can be kind of iffy in some cases. They're sometimes based on estimating the molecular weight of the protein and so on, but we would like to be able to check those values against something else. And one of the ideas that we have been working on with the Sachs group at EMBL Hamburg, and especially with Anne Tukkanen in Dimitri Svergan's group, is to try and use Sachs. So if you have a sample where you've got both EMDB and Sachs data, could we use the Sachs data sort of to see what the best contour level should be? So I should mention that there is the so-called SAS BDB, which is a public archive for small angle scattering data. And in conjunction with working with Anne, we have developed the software to calculate simulated, or I shouldn't say we, they have developed software to calculate simulated Sachs profile from an EM map and a given contour level. So this requires a contour level to calculate the simulated Sachs value. So the idea that we are working on is to try and match the simulated Sachs profile with the real Sachs profile while we vary the contour level. and then compare the optimum contour level with the recommended contour level. What type of validation tools we use for SACS data? I have no idea. So I think that would probably be something which we would have to ask the SACS people. I mean, we don't actually accept any SACS data ourselves. From what I understand from what Anne is doing, so they're actually trying to use some sort of FSC-based methods to do some sort of validation of the SACS bead models and so on, which they are acquiring. But I think that's still in very early stages, so there's nothing I think which they have available online yet. On the another collaboration that we have with, this is again with the Madrid group, so they have developed something which they call 3D bionotes. And this is again something which is quite nice in terms of, so for EM entries where you have a fitted model, what we will do is provide links to 3D bionotes. And what this essentially does is that this provides you with additional annotation in terms of sequence annotations, protein sequence annotation, as well as gene annotation. And it's quite nice and interactive in the sense that you can highlight an area or region in the structure here. It'll highlight similar regions in the protein annotations and in the genome annotations, and vice versa. You can highlight, so if you're interested in a certain sequence, you can highlight it here. It'll highlight it in the 3D structure as well as in the genome data. So yet another thing that we are, I would say that this is at very early stages, but this is also something that we are thinking about, which is to look at, so just the visual perception of maps. So I showed you earlier for the apoferritin, so you had the low resolution structure, then you had the Lori's and Chris's structure, and then this, so this was 4.7, this was a 3 point something. You can visually see that these surfaces look different. So this is smooth, you have more structure to this, you have yet more structure to this. And one of the things which we were interested in examining was just look at surface properties of the surface, and to see how this correlates maybe to the level of detail that we think that it's compatible with. And this is something that could be used even when, because this is based mainly on the surface, this could be used even when a model is not available. So this is something that we are working with. It's on very early stages, but it's something that we're working on with Deok-Soo Kim from Hanyang University in South Korea. And just as one example, we could examine things like the surface area to volume ratio as a function of contour level and look at it both globally and locally. So I then want to go on to talk about data integration. And so with data integration, I think one of the key things that we really want to do is that up to now, things which I've shown you on in terms of the services, they're all entry based. So we show you one entry at a time. But from a biological level, you don't really want to focus on entries. You're really focusing on the biological problem, and you want to get all the structural data together. So this is essentially the idea with the volume browser, that we want to get an integrated view of all the structural data on a biological problem from different entries at different scales. So what I showed you previously with the volume slicer, you might recall, is essentially what's being shown here. You have the panel with the 3 orthogonal views and a central view. But what was missing in the volume slicer was the segmentations. And what we didn't have was the rest of this integration, which is that we can essentially, it would be nice that you can click on a segmentation and get related higher resolution EMDB and PDB structures, and then, for example, have integrated 3D view of that. So we have essentially a bare bones version of this, or entry-based version of this. What we want to get to is the volume browser, which integrates multiple entries. And the question is, why should this be that difficult to do? So there are several things which have prerequisites. It's actually quite a significant challenge for us. So one is that to connect the cellular world to the molecular world, we need essentially segmentations, and we have very few segmentations deposited to EMDB, so that's one thing. But we need segmentations which have structured biological annotations as well. So if one person calls something a nucleus and someone else calls it something slightly different, free text annotation makes it very difficult to do automatic linking of things. So we need things like UniProt descriptors or ontological terms which we can use. Another type of linking which goes back to what Wolfgang Baumeister showed you yesterday. So he was showing you, for example, the back projection of subtomograms into tomograms, and that's extremely useful to see how things actually distributed in the context of cells. But in order to do that on the archive-wide basis, we need to calculate the transformation matrices which relate the subtomograms to the tomograms. And although this is being generated and people have it, we don't actually capture that yet. So we need to have the deposition of this. And in order for this to work, there's a lot of work that needs to be done in terms of file formats. So there are multitudes of different segmentation file formats. Almost everyone describes their transformation matrices in slightly different ways. So we need support formats, translation software, web services to help users to convert between these things. And then once we have all of these, then we need also to have a way to overlay segmentations on images for visualization, which is not necessarily trivial. So I should say that we do have funding from the MRC and BBSRC to do this. And one of the steps that we have taken is, so last year we organized a meeting in Cambridge, which this was an expert workshop on 3D segmentations and transformations. And the idea was to discuss some of these issues. And usually when we have workshops, they sometimes result in statements or they don't actually result in anything. But we actually got some very concrete feedback in terms of format development and so on, which we have moved forward with. So the work that I'm showing you here, this is work done by Paul Correa, and he's essentially really done a great work in terms of taking all these objectives and actually translating them into real concrete developments. So one, we now do have what we call the EMDB segmentation file format, which both adds the structural biological annotation and handles transforms between tomograms and subtomograms. So we have one format for both segmentations as well as for transformations. And this was one of the outcomes from the meeting that people suggested that this would be a good thing to do. Formats are useless unless you have the software which allows you to read and write them. So another thing which he's done is he's written the Python scripts to read Sega, iMod, Amira, and convert them into EMDB SFF. And this is no simple achievement. For example, Amira is commercial software. We don't have, so essentially you have to reverse engineer this to actually get the things out from Amira. So we have good progress in converting things into the file format. The other challenge was then, if we have segmentations, we need to be able to display them in our browser. So again, there he's made a lot of progress in terms of we have this working, so we can display segmentations in Omero, which is what's being used as the backend for the volume browser. And I should also mention that once all of this is available and up and running, we'll make it a public open source distribution. probably through the CCPM, which I encourage people to use. So if you then go on to looking at some of what I think some of the future challenges and opportunities. So I think for EMDB, I think there's a very strong trend that tomography there's a lot more use of tomography and subtomogram averaging. And I think there's a lot of enthusiasm after people have seen where things can lead recently. But this also highlights the importance of integration between the cellular and molecular structural data. So I think it's really nice to have, for example, subtomogram averages of ATP synthase, but what would be even better to have is to be able to overlay these on the tomograms showing the ridges and so on, which people have shown in the context of the tomogram. Another thing which we have to contend with is that the field so this is not a static field, it is changing very quickly, and we need to keep up with this on the archiving side, and I think this means that we have to make changes to the data model as well as to allow different types of data to be deposited. So here I need to be slightly apologetic, because I think for the last year or so, every time people have asked me to make a change, I've always said that I'm sorry, we can't make a change right now. And the reason is that we went live with the new WWPDB deposition system, and there were quite a few teething problems which we still work with right now. So until that has settled, but things are starting to get better, we'll then have more time to start making these changes. But I think some of the types of changes that, we've seen, for example, different ways of tilting the specimen in different schemes of tilting the specimen in tomography can be important. For example, the Hagen scheme, which John Briggs uses. So capturing enumerations on this is important. I have a long-standing issue about 3D electron crystallography. So I know that Tamir Gonen is extremely annoyed that when he deposits his 3D electron crystallography in EMDB, it's still classified as 2D electron crystallography, so that we don't distinguish between 2D and 3D electron crystallography. We have updated that, but it's not reflected on everything that we show. But these are the small types of things. So 2 years ago, no one talked about 3D electron crystallography, and well, maybe at least not, it wasn't widely considered, but now we are getting regular depositions of 3D electron crystallography. Okay, that's a point to consider. Yeah, I think right now we still, in the new model, we have 2D and 3D, but on the data outside we could just collapse that into one.
If you will just combine together with what's going on in material science, it's all the time was reflected and linked to three-dimensional analysis. But nonetheless, the concept of electron crystallography is very broad, and therefore just that it's really limitation of biological sciences when they have been limited just to 2D crystals. It was just convenience for the using electron microscope, but it doesn't mean, for example, from the concept of electron microscopy in general, it just has to be electron crystallography. Okay. That's it. And what you have got and what you have used as an input data, it's a particular problem in this given research.
Okay, point taken. I think that's something that we can consider. New types of data, so segmentations, transformations, new types of validation data. So all of these are things which, as they come along and as they get important, we need to start accepting it. One of the things which I think is still archiving of hybrid methods is still a challenging problem. So I think there are no clear ideas here in terms of how this is going to be done, and it's still a very open issue. So with Empire, we are expanding to include other imaging modalities. So we have already started to accept 3D scanning electron microscopy data as well as soft X-ray tomography data. We are working with the correlative light microscopy community to understand the correlative data, but we haven't accepted any data sets yet, but I think that'll come on a little later. I often get a question of whether we would be trying to push for getting the deposition of raw data mandatory. I think we want to work with the community, so we won't push it too hard. So we would prefer sort of gradual change of the mindset and see that things evolve a little bit as it has with the EMDB as well. I think one thing which will help in terms of getting more depositions is if we develop harvesting pipelines, because this would make it much easier to get data from major microscopy centers like Diamond. So not only for Empire data, but also for EMDB data. And we have a sort of initiative with the CCPM to look into harvesting especially from Diamond. Something which we also have to consider is that we're starting to see data sets which are crazy large in the sense that, 10 terabytes is small, but this is often from the K2, and with the K2 there is the prospect of doing lossless data compression, so we are looking into different ways of doing this. I think with Empire we also have the challenge that in terms of funding, we have funding to the September next year, so we are applying for a renewal, and we need both community support, but also we're looking for ideas in terms of how to continue this. And finally, in terms of China, so China is a real special case for us because the links from the UK to China are really good. So there should be high-speed links. And 2 years ago, there was a great fanfare in the UK and China with the governments shaking hands and patting each other on the back because they had established this real high-speed link between the countries. Then you had the Great Firewall of China coming up, and it means that they cannot download our data and we cannot access their data. So the question is, how do we go around this problem? And one idea which we have been working with Chinese EM groups is to establish a sort of mirror of Empire and EMDB in China to make it more accessible and easier to access data in China. So I should point out the EMDB mirror in China will probably only be useful for China because China is not a good distribution center for anyone else. On the validation side, we have we've had a EM validation task force which sort of provided guidelines in 2010 as to what would be good to do in terms of developments and so on. And I think with the validation reports now going online, it would be useful maybe to have another EM validation task force meeting. So I think it's not completely decided, but it's kind of on the agenda for possibly next year to have another EM validation task force meeting. Half maps can now be uploaded as a specific data item to EMDB, and this allows you to do things like, so we could start calculating FSC curves ourselves as well as doing the ResMap analysis. You can already upload masks, but if we would need to have a specific data item for that, but we could also then do things like what Shor Sheres has described as the masking compensated FSCs. We need to define more data models for collecting the results of, for example, the tilt band ResMap analysis at deposition. And I should also mention that for ResMap, there's a very practical problem of size. So maps which are greater than a certain size don't work. And unfortunately, I don't think that there's anyone working on this right now because I think there was no funding. So they had looked for funding to allow them to do this, but that didn't go through. There are also ideas, for example, that have been suggested by the Karatso group, for example, to run validation against raw data itself. So this would be automated validation against, for example, data which has been deposited to Empire. These are things which I think are very challenging because first we need to have more consistency in what is being deposited and be able to link between the Empire data and the EMDB entries and so on. So, but this is something which may come online gradually. And as I have shown in many of the slides, so we work with a lot of different collaborators, and if there are new ideas and we welcome new ideas and collaborations, especially on things like validation. I want to again thank Natesh for inviting me here because it's been an eye-opener to see, just to understand to get a better understanding of the situation with EM in India, and we do want to help and serve the community. So if there are issues in terms of deposition and so on which are specific to India, we would really like to know that and about challenges. And again, if there are people who want to collaborate in terms of methodology developments along the lines of validation and so on, we are also interested in that. So I think with that, I just want to thank some of the people that have worked on this, as well as our funders, and so almost everyone funds us. So we have MRC, BBS, RC, EU, NIH, EMBL, and the Wellcome Trust. And I was a bit surprised because I think this is the new Wellcome Trust logo, and this one is well, I thought that they changed the logo, but I might have to go back to the old one. In terms of people involved, so Gerard is the team leader for PDBE, and the EM group, I mentioned some of the people already. Andre, Paul, and Eduardo in particular have been working on some of the things which I've shown you. We have good connections with Birkbeck, especially Maya Top's group, and Agnel. We worked with them as well as with Helen. Wachu at Baylor is our partner for the EM Databank project. Kathy on data deposition. At Francis Crick, Lucy and Rafaela work with us on cellular data, so they've been very helpful in defining things like data models for scanning data and so on. On CCPM, the STFC and Martin Wynn and Tom have been very helpful. And then Dundee, this is the open microscopy environment. So Jason and Josh, so these are the people who provide the front end of the browser that we showed you. At CNB in Madrid, we have Jose Maria Carazzo's group, and we have a number of people here who have helped us. Gabe at Scripps, Duxu at Hanyang, and I should say that this is just a very small list of very many people who help us, and we have a lot of people, for example, at LMB and other places who have also been very helpful with us. So with that, I would like to thank you for your attention. Any questions?
Good. Thank you, Arjun, for a nice, extensive introduction and details of deposition and validation in EMDB. And questions, any? Jayati?
Yeah, I just want to know that you said that there is one NIH EM data bank. So we can deposit in EMDB either or NIH or something like that? I'm confused with that.
Okay, so the archive is EMDB, and the data ends up finally at EBI. But we have deposition sites both at, so you can deposit data at EBI, You can deposit data at RCSP in the US. I think because you're in Asia right now, so by default your depositions would go to PDB Japan.
Okay.
But ultimately the data will end up in the EMDB archive. Yeah.
Okay. And another question I just want to know, when we download, say, one particular, say, ribosome maps from different groups, they are not aligned most of the time. Their origins are different. So I knew that there was a, I think, software or a server made by Roland Bakeman's group probably to align. But I don't know, is there anything from EMDB that we can use?
Yeah, sorry. That was one thing which I didn't mention. So we do have a service called PDB Shape, which is a shape matching server, which what we have essentially done is we have aligned structures in EMDB to each other. And in fact, we didn't manage to align all the entries in EMDB because there were too many entries, but what we have aligned are the ribosomes as well as the chaperones. So if you're working on ribosomes or chaperones, you'll be lucky and you can get them aligned to each other. So you can
already aligned, you mean?
They are pre-aligned, yes.
Okay, because
I can give
something, say maybe a year before, and they were not actually, some maps.
I would be happy to provide you a link to the server.
Okay, thank you.
Sarjit, anybody else?
Just one question. You just showed the example of a file that movie stacks are aligned, but are they gain corrected or not? I mean, is it required to gain correct them?
Yeah, again, it's not prescriptive. So we have gain corrected micrographs and we have non-gain corrected. I think on hindsight, the fact that you can compress non-gain corrected images better than you can compress the gain corrected, we would prefer probably to have the non-gain corrected. So we may, once we have analyzed this completely, we might start recommending people to give us the non-gain corrected images.
Is it like annotated in the file that is gain corrected?
No, there isn't any annotation, so that's also something that we could add. Yeah.
If there are no more questions, let's thank Ardhan for a nice talk. And this is the end of all the lectures in this course. And I had a good time with all of you. We will have a evening session. I want everybody to come at 7 after the practical sessions. We have, oh yes, forgot again. So after the practical sessions, I want everybody to come here at 7 so that we can distribute the certificates. I will request Elena to distribute the certificate at that time. And yes, I would like to thank Ardhan for the talk. Please.
Thank you.
Come in the center, that's what they say. This is again a memento for the course.
Thank
it's
you.
Ardhan mirror. Metal mirror. And yeah. What alloy, I don't know, it's a mixture of some alloy. Thank you, Ardhan.
Thank you very much.
And we will be happy to help you in the AMDB perseverance in the future as well.
Thank you.
And community is going to grow, I am sure, in India as well, so we will be actively involved in it. Thank you.
That's great to know. Thank you.
Lunch and 1:15, 1:30 we'll leave here.
EMDB map as well as model challenges. Yeah. Can we download it and use for
Yes, the
purposes?
map challenge data can